Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous video, we learned that our sample may not represent the population, but non-random sampling isn't a single problem. There are many different ways a sample can become non-random, and each will lead to different econometric challenges requiring different solutions. Now, this video builds that roadmap. By the end, you'll know which type of problem you're facing before you decide which tool you'll use. If you remember, we said that from the population to the observed sample, there is a selection process. So every study begins with the population, goes through a selection process, which determines which observations appear in the dataset. And if the process is random, great, we've got a representative sample. If it isn't, we need to understand exactly how and why observations are missing. So we kind of touched upon all of these different methods in the previous video, and we've got sample selection, truncation, censoring, self-selection, attrition, convenience sampling. So as you can see, there are a lot of them. These are the most common ways a sample becomes non-random. They all involve missing or incomplete information, but they are fundamentally different problems. So treating one as another, it's going to lead you to wrong solutions. Let's start with sample selection. In here, whether an observation enters a sample depends on some characteristic that is often related to the outcome that we're studying. For instance, do you want to estimate wages? Well, only employed workers appear in the dataset because that's the only way you can get wages on the workers if they are working, which means unemployed individuals are completely absent. Okay, the selection into the sample being employed is related to the common outcome in here, which is wages. So it's this connection that is creating the bias ultimately. And by the way, this is the most important type for this mini arc as well. We're going to see in other videos the Hackman correction, which was specifically developed to address this problem. So for now, just keep in mind sample selection related to the one of the variables and the most common one. The next one would be truncation. With truncation, what you're doing is that you are literally only picking certain values. So you draw in, let's say, income distribution, and you have people below 10,000, which could be completely missing, and above 10,000 are the only ones that are observed. So with truncation, observations outside a certain range never appear in the data set. Okay, they are completely invisible. For instance, a survey that only records household earning above 10,000. Everyone below that threshold simply doesn't exist in the data. Okay, and we don't even know how many observations are missing or anything about them because they don't exist entirely in this data set. So truncation as a problem is actually quite severe, and if compared with censoring here, truncation is even more severe than censoring. With truncation, the observation is literally gone. With censoring, which is what we're going to look into next, it's still there, it's just partially hidden, okay? So what happens with censoring? Let's say your true income with censoring is 5, 10, 15, 20, 25, and 30, okay? Let's say that the one that's recorded is actually 5, 10, 15, 20 plus, 20 plus, 20 plus, okay? Now, with censoring, observations still remain in the dataset, but we don't observe their true value beyond a certain limit. So as you see here, we always had this 20 plus in here. For instance, a survey records all incomes above 100,000 simply as 100,000 or more. And these individuals are still in the data, we just don't know their exact income. And this is that crucial distinction from truncation, because in truncation, observation is gone, it disappears, okay? In censoring, the observation simply stays hidden, it's clipped, the actual value. Top-coded income variables in administrative data sets are a classic example of censoring. Social Security earnings records, for instance, in the US, there's a cap reported earnings at the taxable maximum. Everyone above that threshold basically appears as the same value. The next one is self-selection. For instance, people self-select to participate in certain job trainings, for instance. They are the ones who have the last decision. So the question would be, are participants likely to be similar to non-participants? And the answer will be, well, usually not. It's mostly the highly motivated people that will enroll into the programs. So the decision to participate is what creates a non-randomness, okay? So decision to participate. Now, self-selection is closely related to sample selection bias, by the way. The difference is that here the individual makes the selection decision, whereas in pure sample selection, the researcher or the data collection process determines who is actually included. So very similar, is just the who decides it that makes a difference between the two. We've got attrition, which occurs in panel and longitudinal studies when participants drop out over time. The study, like for instance, a study that follows individuals for 10 years, some may drop out, they move, they stop responding, or can't be tracked. And the question would be, are those who remain still representative to those who left? And the answer, unfortunately, is not always. For instance, lower income households may be harder to track. Sicker patients may drop out of health studies, right? So the remaining sample drifts away from the original population in this case as the study progresses. And attrition bias is one of the most underappreciated problems in longitudinal research. A study that starts representative can become systematically biased over time simply because certain types of people are harder to follow. Okay, so loss of participants over time. And last one, convenience sampling, which is serving, let's say, students in classrooms. Can we generalize results to all university students? Probably not. The sample was chosen because it was easy, not because it was representative. And convenience sampling is the most straightforward form of non-random sampling and also the most common in practice. If we were to summarize all of these problems in a table, so this would be how you should be thinking about it. You've got the type of problem, you've got to think what's missing, and you, like as we mentioned earlier, examples for each and every case of these different selection, like different non-random sampling issues. Keep in mind, same umbrella, non-random sampling, but very different problems, okay? And this column right here, what's missing, this is the most important bit of information that you have to keep in mind because that is your key diagnostic question, okay? We'll focus on three that are most common in this mini arc, and we'll have like well-developed solutions. We're gonna mainly concentrate on sample selection, truncation, and censoring. Self-selection will be covered as part of the sample selection discussion since it's closely related. Attrition and convenience sampling are important to recognize, but will be beyond of what we'll be doing in this little mini arc of non-random sampling, okay? Before we conclude this video, I'd just like to point out a very common misconception about non-random sampling, and that is all non-random sampling problems are examples of sample selection bias. Okay, so this is a misconception. Okay. As we saw, the sample selection bias is just one specific form of non-random sampling. We've got truncation, censoring, and so on, okay? Now that we've mapped the landscape, we're ready to start the first and most important type, sample selection bias. We'll begin by understanding why selecting only certain individuals into the sample can bias our conclusions, even when the regression itself is perfectly specified. So stay tuned, and I'll see you in the next video.